So the point of the Hess Law Lab is to prove that the processes is gonna the heat produced by the processes is gonna be adding up and equals to the heat that was produced by each part of the um, factor. And the equations we're going to be focusing on are these three right here. And the only reliable information that we are having are such over here, where they gave us a density, a molarity, and the heat capacity. So we're going to have to use these information to backtrack that way using these each ones to get the H by using the fact that the heat gained by one is the heat lost by another. So let's focus on the middle equation, the heat produced by the solution, because the other two is pretty straightforward. So I think once we get through this one, it would be pretty apparent what to do for the rest of them. So the equation says that we have the specific heat of the solution times the mass of the solution, and then we have the change in temperature. The capacity, heat capacity of the solution is given on this slide, on right here. So that's just a given at 4.0 joules per gram Celsius. The delta T here is going to be from your graph, and we can cover that in another different tutorial. But what I want to focus on is the mass of solution, because that's one that is not just straightforward, straight apparent of what they are. So let's dig into that a little bit. We know that the chemical reaction taking place is such. We have sodium hydroxide, we have a hydrochloric acid, and that those produce a salt and water. And we also know that this is aqueous, meaning that whatever volume we come up with, the total volume of that is the same as the salt produced, meaning the water weren't in vapor forms or in solid form, if they could have possibly been, that everything that was produced is going to turn into NaCl aqueous. So let's go ahead and set up our table of molarity, which is going to use the relationship between the volume and the molarity of the reactants that we use to make what we want, which is going to be your molarity of the salt, your volume of the salt, and your molarity of the salt, and then also the moles of the salt. Now I'm going to be using the numbers that my group produced, and here you're going to have to put in your numbers. And keep in mind that the correct sig figs is going to be important, because that's going to affect the final mass that you have. So for us, the first, the NaOH was at 50 milliliter, and so was the HCl. But we have to convert that into liter. And then for the molarity, we have for the NaOH was 1.198, and for the HCl we have 1.113. And then, so therefore, when we go to the moles, we'll see that going down the chart, this is multiplying, and I'm going to pull out the calculator and do this calculation actually. I probably should have it written by now, but that's okay. So we know that this is at 0.0599 moles. And this is going to be at 4 sig figs. So we have to add a 0 there. And then the other one is going to be 50 times 1.113 divided by 1,000. That's going to bring us to 0.05565. 4 sig figs again. Now, here we can see that clearly, because they're all 1 to 1 to 1. Therefore, whatever reactants have less mole would be the limiting reactant, and in this case for us is the HCl. That tells us that our moles is going to be the same as the HCl, a mole of the salt or the salty aqueous solution. That also tells us that by doing so, we'll have this plus this. Actually, as stated before, we saw that, because it's an aqueous solution, the water doesn't stand alone, so all the volume of the original solutions are going to become our NaCl volume, which in this case for us was 100 then, milliliter. So I like to change this into liter as well, because that's going to come into play later. So I just want to confirm, but I could have just moved to the decimal point, but it's also going to tell me it's 10000. And again, keeping the sig figs is very important. Now, having these two information, we can go ahead and calculate the molarity of this thing. So, because it's in the middle of the chart, and we know that moles divided by liter is the molarity, so we can go and do that. And at there, you are going to find that the molarity is 0.5565. And again, keeping sig figs because that's the smallest sig figs. So I'm going to take a minute here and record these for myself for later. Then we have 0.5565 molarity, and then we have 0.05565 moles. Now, we are going to go in and use the density that was produced, because now that we know that our molarity is very close to the OM, but we're not actually 0.5, we're going to need to extrapolate using the density information, the relationship between these two, and get the actual molarity that we have. I mean, actual density that we have with the volume that we have. So we do know that we have 0.5 molarity, and that's the same as 1.02 grams per milliliter. Now, we also know that our actual molarity is 0.5565, and we are going to try to find X, our density. And that simple algebra maneuvers, you're going to find that I can't even do simple algebra maneuver right now. Okay, so we have X 0.5 equals 1.02 times 0.5565. and then we're going to divide that by 0.5. So x is going to equal to that whole thing. 1.02 times 0.5565 divided by 0.5. 11.5. Oh, copy that wrong. It's actually 1.3526, as in gram per milliliter. Now this is where I'm a little fuzzy, because technically this would be 1 sig fix, right? And if we take 1 sig fix here, it's gonna tell us is, 1 gram. What am I doing here? Here we go. So it's going to tell us it's 1 gram per milliliter, which is going to be less significant than the given density. So I think, ignoring all the sig figs, we should just go ahead and call it 2 decimal place. So we're going to go ahead and say that that's not true, and the actual density that we are going to use is 1.14 gram per milliliter. And this number can change based on what your calculations were. But as long as you follow the steps, you will get here. And also note that when we do the calculation, you should use the unrounded number. This would just be a number that you put in the table and report, but this should be the number that you use to go through all the calculation. So again, I'm going to write this on the side, so I have that to use on the side later. Now that we have density, we can go ahead and find the mass, because that's what we're after the whole time, right? And so we're going to come back down here, and we're going to say, well, we're not going to say, we know that mass is in gram. And we also know that we have molarity, which is mole divided by L, which is liter, the volume. And then we also have the density, which is gram per milliliter or liter, which we can convert to. We also know that we have the volume from the table, and we also have the moles from the table back here, right? So now we're going to go in and do the calculation by saying that, because we want the grams, right? So having the moles is going to cancel this out. Having the volume is going to cancel these two out. Fine. Thank you. So we know that mass is going to equals to gram times milliliter. Convert that into liter, and then we're going to have to divide it by the molarity. Right, so this is a really tricky part, and this might be a little tricky as well, but we're going to get through that. So, as we said, we have density, which now for us is 1.3526 gram per milliliter. Of course, we have to convert it into liters, because our volume were in liters. Our molarity was in liters. So now we have to put in per 1 liter, the molarity was 0.5565. So let's go ahead and do that calculation real quick and see what that brings us. So, okay, I just got a huge number, so I don't know if this is right. I'm going to redo this calculation. Okay, so we're going to go ahead and go with this number. So this should be our mass of the solutions, or better yet, this is the mass of NaCl in solution. That sounds like way up. So I might have to go back and revisit this, because if we do this wrong, then this gets wrong, and that implies that when we get to here, this whole thing is going to be wrong. So we should look at our process and see if there's any place where I actually did this wrong. And if you did find something, please let me know. So now we do know that Q solution plus Q calorimeter and plus Q reaction is going to equal to 0, because one, the heat gave off by one is going to take up by the other, and total heat, we didn't create any heat. Basically, that's the point of this lab. And we know that the Q solution is going to be done by punching it into here. But I'm just going to write the long form so that we don't have to go through that calculation. And we know that the Q calorimeter was the calorimeter's specific heat times the change in temperature. And this was given. And then we also know that at the reaction, we have the change in heat times the moles of the molecule that was reacting, which for us is going to be back here. And so we're going to go into how to set this thing up and try to look for this heat. So recall, right, this is the equation. Oh. This is the actual equation, and these are just individual components. So we're going to go in here and say that if we move everything but the Q reaction on one side, we'll have change in heat of solution minus the change in heat for calorimeter. And these two things, or now we're going to break them down, which is going to be that times the moles, and this is the MC, change of temperature, minus C, change of temperature. And we're going to divide both sides by moles. And for that, we will have the change of reaction and equals to the mass of the solution, which we went through and got, and the specific heat of the solution, which was given, and the change in temperature, which is the thing we got from the graph, and we have the specific heat of calorimeter, and which was given, and the change in temperature, which is the same thing from the graph, divided by the moles of NaCl produced back then. So by doing this, make sure we have the negative there. By doing this, we'll find the change in heat of specific of the reaction.